All right. Well, good morning, everyone. It's about 9:03 here in Ann Arbor. I want to welcome everyone to this morning's workshop. Thanks especially to those of you who are joining here in person. We have a lot of people online as well, so thanks to those of you who are joining via Zoom. My name is Brady West. I'm the director of the Scientific and Technical Core of the Population Dynamics and Health Program. So we want to welcome everyone to this morning's workshop. We're definitely very excited about this topic and especially about our presenter today. I wanted to start just by saying a little bit about PDHP and some of the services that we offer. So the Population Dynamics and Health Program that you see up on the screen, this is an infrastructure. It's an infrastructure center supported by the National Institute for Child and Health Development at NIH. We are responsible for providing research services to the ISR, the university as a whole, and then broader external affiliates of our program. So some of you may be joining from other locations. We'd be happy to work with you moving forward. We offer a variety of services. These workshops are just one of them. So we have a number of workshops coming up over the course of the summer and into the fall. And at the PDHP website that I have open right now, if you go to the workshops tab, you can see today's information about today's workshop, but also a variety of links to past workshops that we've put on, and also our YouTube playlist. So all of our workshops are recorded, materials are available online, so you can go to that YouTube playlist and see a history of all the other workshops that we've offered and catch up on other topics that you might be interested in. So today's workshop is going to be recorded as well, and eventually that'll make its way up onto that playlist. We provide consulting services to our affiliates. So if you're in need of help with statistical analysis, research design, data management, working with secure data, we have a small team within the scientific and technical core that would be happy to help you out with that. If you're interested in becoming either an internal affiliate here at the University of Michigan or external affiliate, if you're from another institute, we'd be happy to talk to you about that process. We have information about that process on the website here as well. So we provide these workshops, we provide that kind of consulting service. We're also available if you have funding for research and you have funding for analytics support or data management, we'd be happy to talk to you about setting up subcontracts to help you with your work. So we have analysts, data scientists, statisticians who can help you with various analytic, quantitative, qualitative aspects of your project, whatever the case may be. Definitely let us know if you'd be interested, and we'd be happy to talk to you more about that. So that's another one of the services that we provide. We also offer a small grant program. So if you're interested in applying for a small grant to help support your research, whatever aspect of research infrastructure you might need help with, feel free to check out our small grants page. We have some rolling applications that you can apply to if you'd be interested in various amounts of funds to help support your research, but you can read more about the areas that PDHP supports, and the types of small grants that we've awarded in the past. We also have a variety of endowment funds here at the Population Study Center at ISR where we could help to support your work via those funds. So certainly take a look at that webpage if you'd like to read more about some of the small grant opportunities that we offer as well. And then again, there's a variety of other resources describing what PDHP does up on the website. So feel free to reach out to us. You've probably heard from Paul via the announcement for this workshop. Probably easiest to email Paul to get in touch about some of these services, but we'd be happy to hear from you and talk more about these services moving forward. Okay, so let's move on then to today's workshop. And we're going to turn it over here to Eitan in a second, but I wanted to introduce him briefly. So very happy to have Eitan here today. So Eitan Adar is a faculty member in the School of Information and Computer Science and Engineering here at the University of Michigan. His work is largely in how to embed AI into user interfaces. And he has an emphasis on applications in visualization, education, and creativity. So again, Eitan, thank you very much for being here. Very happy to have you. We're looking forward to today's workshop. And we'll go ahead and get started. I'm going to turn it over to Eitan. If you have questions, feel free to enter them in the chat. Paul Schultz is going to be monitoring the chat today, and he'll bring questions up. We'll have breaks to answer some of these questions, and we'll really kind of play it by ear and see if you'd like to go on the fly or how that goes. So we'll see how that goes. But feel free to ask questions in the chat if you're online. If you're in the room, feel free to raise your hand and ask questions, and we'll go from there. So, okay, so Eitan, I'll turn it over to you.
Thanks. Thank you for the introduction. Okay. Hi, everyone. Is it registering okay? Okay. So, hi, everyone. Thank you for attending in person. I see that there's quite a few people online, 90 or so. I'm happy to take questions as we go. I'm used to lots of interruptions, and if there are things you want to know more about or less about, just, demonstrate it by raising your hand or looking bored or whatever. I'll figure it out. This is a condensation of more than a semester's worth of material into about 4 hours. So we're certainly not going to be able to cover everything, but I did want to talk about some of the high-level concepts and hopefully give you some new insights into how to use visualizations better in your work. So yeah, I've done a lot of work with very large scale data sets. That's how I came into doing this kind of work. So I started by doing work with large network data sets. So how information and memes flow and mutate through networks like Twitter, Facebook, how Wikipedia structures are formed and so on. So I've done a lot of work with text and network structures, and lots of work with very big data sets. And as part of that, there was often a need to do visualization. So I started many years ago coming into the visualization practice and built many programs and many user interfaces and built a number of new encoding techniques for visualizations, for uncertainty visualizations, for networks and so on, that are still in use today. So that's how I came into doing this. And where my research still is. So you'll see a little bit of the research that I do when I talk about how to use learning objectives to figure out how to best communicate your visualizations. That's a recent project that my group tackled. But again, this is like based off of multiple classes that I teach at the university. So I teach an information visualization class for graduate students. So if you ever want a semester-long version of this, you are welcome to register, I suppose, or send your students to me. There are other people who teach it now, but there's also an online Master of Data Science version where we have split it up into 4 6-week chunks that cover different topics. So that's another way to get more of this if you're interested. So at the bottom of this page, for those of you online or in the room, there's a link to a GitHub site. So it's github.com/eitanadar/PDHP 2025. There's not much there. There's a bunch of links. I will put it up again later if you are interested and want to go look and follow along. There's a PDF version of the slides as well. There's nothing in there right now that you sort of need to look at, but if you're interested in sort of finding out more, that's where you can go. Okay, so that's the about me. I guess it'll be a little bit hard to do the about you section, but maybe the people online can do the raise hand feature and the people in here can raise their hands too. I assume many of you are self-selecting and interested in visualization, so I'm not going to ask about that. I guess I'm curious, how many of you know what this is? How many of you have seen this visualization? Okay. I don't know, you can tell me sort of online if you want to raise your hands. Some hands raised. Okay. Okay, so some. All right, so how many of you know what the good points of this visualization are? Oh, no one wants to admit this. A few, okay. All right, so I see probably a few Tufty fans in the audience. How many of you know what the problems with this visualization are? Okay, that's good. All right, so this is a starting point for me. So I will come back to this a little bit later. This is, for those of you who don't know, this is Edward Tufte. He's a famous sort of a writer of visualization books, whose books have become sort of law in the visualization community, but I somewhat disagree with. We'll talk about that in a minute. This is his favorite visualization. This is Menard's map of Napoleon's march across Europe to Moscow. So what you're seeing is the army. It's kind of a Sankey diagram, the army marching from France to Moscow and then retreating. The size of the line is the size of the army, how many people are still alive. The bottom is reflecting the temperatures, so sort of the freezing cold as they retreat and die off. And you can see the underlying map, so their location. You can see the size of the army. You can see whether they're going forward or backward, and you can see the temperature. So Tufte loves this because it has lots and lots of information embedded in it, but it does have some problems, which we will get to in a minute. But this is a very interesting visualization of old classic visualization. Visualization itself, I'll talk about this in a minute, but it doesn't have a very long history, relatively speaking. It's sort of a new idea as we sort of mastered statistics and so on. But let me talk about what we're going to cover today. So I will take breaks for those of you in the room. If you need to get up, stretch, go to the bathroom, whatever, and it's not a break, just do it. It's fine. I don't mind. My students do this all the time. But I will try and take breaks for those of you who are online, and we'll do some stops. The three topics that I want to cover today, and these are kind of going to be the three major chunks. I want to talk about InfoVis at large and perception and cognition and sort of why visualizations work. This will help you, in part, understand why certain techniques work and others don't. It will help you make judgment calls about why one visualization technique is better than the other. We're not going to get through everything. This in itself is a semester-long thing, and I can send you resources if you're really curious about it. But it's really interesting to understand the limitations of the human eye, the human brain, in understanding visualizations and making our decisions about how to pick these. I then want to talk about communication through InfoVis. So many of you probably use InfoVis on a daily basis for analytical purposes. So you're doing analysis and looking at visualizations. Some of you are translating those visualizations into something that's communicative. That is, you're trying to convey information to an external audience. That may be your principal role, I don't know, but most often people start doing analytical visualizations and then move on to communication. And there's a difference there, and we'll talk about what the differences are, because the things that work well for analysis do not necessarily work well for communication. So I'll give you some tools to think about how to express your intent with visualizations, like what is it that you're trying to convey to your audience, and then to determine whether and which visualization does that best, and then figure out if you're actually right. And at the end, what I want to talk about is a few unconventional approaches. So you probably all use bar charts. Some of you probably use pie charts unless you've been made allergic to them. I know some of you have probably been told never use pie charts. I don't believe that. There's reasons why they're good. But there are many, many techniques that are highly specialized that I do want to cover and give you at least a taste. Okay, so there's many, many different ways to visualize time series. There's many ways to visualize multi-series data sets. There's many ways to visualize networks or hierarchies or whatever. I'm not going to cover all of them, but I'll give you a little bit of a sense of alternatives to what you've probably seen. Okay, so you've probably seen standard time series. You've probably seen standard social networks. I want to give you some alternatives that may be better for certain kinds of tasks, either in analysis or communication. Okay, so let's start with InfoVis at large, and let me explain when I talk about InfoVis what I'm talking about and what I'm not talking about. There will be overlaps with other domains, and I'll talk about that in a second, but it's important to think about, from my perspective, the high level, the visualization is this: the use of computer-supported, interactive, visual representations of data to amplify cognition. Okay, so that's a high-level definition that we use. Unfortunately, that definition includes things like this. So this is an example of scientific visualization. This is a methane flame simulation. This is considered a scientific visualization. It is visualizing some real-world thing, okay? Simulation with false color applied. So this is what we call scientific visualization. It is a representation of a real-world artifact. Could be a map, could be a physical phenomena, whatever, that has been modified slightly to make it more readable or more usable. Okay, so again, methane flame simulation. The information visualization that I'm going to talk about includes an abstraction. That is the use of computer-supported interactive abstract visual representations of data to amplify cognition. That is, we will translate real-world data into abstract representations, marks on the screen that do not actually represent directly the thing that it is. So it will not look like a methane gas flame. It will look something like this. Okay, so we are representing here the communication between people in email. So on the x-axis at the bottom, these are email messages that are happening between two individuals. And so every time there's a little blip, it's called a rug diagram or whatever you want to call it. There's a little blip that is an occasion where somebody has sent an email, where there's an arc, one of these red lines, that is in response to something that you received previously. So this is an abstraction of the underlying data set. And what this allows us to see is sort of the repetitive patterns of how often we're communicating in short-term bursts versus long-term communication bursts. Turns out that if you study sort of social communication through email, people tend to have this tendency to mirror each other. So if you respond quickly to somebody, they'll respond quickly to you. If you take a long time to respond to them, as Paul knows, because I was very slow, I'm sorry, it takes them a long time to get back to you too, which is fine. So there's sort of this mirroring effect. And visualizations like this help you see that, okay? You usually generate many of these to sort of understand this, but this is an interesting kind of abstraction of the underlying phenomenon. This is another one. This is a visualization from Dave McCandless, who's kind of a famous data visualization designer. He used to be a journalist, now writes kind of visualization books and awards the Information is Beautiful awards. So it's a very pretty kind of visualization, which gets a lot of flack from some circles. This is how responsive people were in the news to different perceived catastrophes. Okay, so these are catastrophes that never sort of manifested as actual catastrophes, like the year 2000 bug and the bird flu and whatever. So how much attention did they get in the press versus how much, so how much attention did they get in the press over time at different time periods? And you can see at the bottom again, we have time. And again, these things are things that never sort of manifested as being as big of a deal as we thought, but it was interesting to understand the press's response to different kinds of events over time. Again, an abstraction of the data. We are measuring, we are counting something that is the number of articles in the news, excuse me, about each of these topics, and then visualizing it as this kind of stacked time series. 3D time series, more accurate. So our focus will, in this kind of conversation, will largely be digital, on screen, flat. But there are visualizations that people have attempted that have been 3D, dynamic, physical. This is a proteome, like a network of connection of different enzymes, proteins. This is another interesting example. I don't have a video of this here, but this is actually an animated kind of sail visualization. So each of these sails at the top dynamically changes in response to the underlying data. So like network traffic, how much bandwidth is being consumed. So it's a physical thing that sits in a room, and as the data is coming, it moves and changes. There are also physicalizations that are used for accessibility. So I won't talk a ton about accessibility today, but this is a huge problem in information visualization. Our assumption that people are able to see what it is that we're producing on screen and see it accurately in the way we had intended is wrong, right? Like there's a lot of people who can't. Even within individuals that are not blind or visually impaired, there is a range of capabilities. So women tend to do better with certain colors than men. There are certain cultures that tend to respond to different colors based on semantic understanding of things. There are ages, right? Like your hearing goes, your eyes go over time. I know this well. And so our ability to sort of convey information needs to be modulated to sort of understand our audience and who and what they're going to be getting out of it. This is a few examples where people have said, okay, we have a blind or visually impaired user. They need to be able to do something with the visualization. They can't see the visualization. Let's 3D print it. Let's get some artifact that they can feel. And there's been other sort of more modern instances of this with sort of touch displays that have the ability to move up and down a little bit, so you can convey information. The resolution of these things is not as good. Your touch is not as good. We'll come back to this in a minute, as your eyesight, as most people's eyesight. And so there are limitations to these approaches, but it is an interesting thing to consider as an alternative to sort of the flat screen displays that we're used to. So that's one thing. So we will mostly be focusing on the flatland version of visualization. So either on the screen or on paper. But a lot of the examples that I'll get to, especially towards the end, will be interactive and dynamic. And the reason for that is that interactivity is kind of this boost on capabilities of the human. Okay, so there's a lot of limitations that exist when we convey information in this flat, unmoving way. So this is the London Underground. I was just in London. It's a great map. It's very visually pleasing, shows you where all the tube stops are. sort of relatively where they are to each other. There's an outline of a map of London, but unfortunately this is not what London actually looks like. The distances between these stations is not really conveyed properly. There's a whole branch of YouTube videos of people seeing whether they can race the tube from station to station. So it looks very far, but like, can I actually get from station 1 to station 2 before the actual train makes it? Because some of these are actually really close to each other, which is not conveyed in here. So you're not getting a sense of sort of distances and location in real world behavior. And so this is a flat version of this. And so what people have built are interesting interactive versions of this. So this is a different kind of map. This is where the train stations, the tube stations, are actually placed where they are physically in the physical real world. Okay, so it's a very different map than this one you can see, right? There's a lot of denseness in central London and sort of it's spread out towards the outside. Okay, so the tool that they built, which is kind of interesting, is an interactive tool where you can click on any particular station and have the map dynamically reorient itself to tell you how long it will take you to get from that particular station to any other station in the map. Okay, so I'll show an example video of this in 1 second, but again, the difference between this map where you can't do that, you can't tell how long it's going to take you to get from station 1 to station 2, that is a constraint, a limitation, a very hard and important consideration when you're trying to build navigational tools for people. And so if you add interactivity, now you're able to go around and click on stations in this map, and the map will dynamically reorient itself. Okay, so the center of the bullseye becomes the tube station that you care about, and everything else reorients around that. So this would have taken many, many maps, right? Like if I wanted to do this for every single tube station, I would have had to produce many, many, many maps. And that would have been very difficult in any kind of form that I would give people. But now that people have cell phones or anything like that, we can add these interactivity features, which will be this great cognitive boost and support a lot more features than this flat map. Okay, so this is why we're going to add interactivity to a lot of our visualizations, is because they will amplify the kinds of cognition beyond what visualizations can do to help answer and address other kinds of concerns. So we'll think through prioritizing different kinds of interaction, as you'll see, based on user needs. So what is it that the first thing that they need versus the next thing that they need? But this is a tool that you should think of as being available to you in your toolbox. There are various related topics that information visualization draws from, but is not necessarily the same thing. So I assume many of you work with GIS software, or some of you, I don't know, but you've probably worked with some GIS software to do maps. Cartography is related, but is not necessarily the topic of interest here. So the kinds of techniques that cartographers use will be applicable to information visualization. Where labels are placed, for example, is very important, and it's something that map makers have gotten very good at. There's algorithms that do this very well, figure out where to place labels on a map, and therefore how to place labels on a visualization. And so some visualization software actually leverages these particular techniques. But again, this is closer to scientific visualization. There is a real world sort of mapping between what is being displayed and the physical real world. Where it becomes a little bit closer to information visualization is where we overlay information. So, so this is like millibar. So this is a pressure overlaid on top of the map. So this is additional information. It's a little bit of a scientific visualization overlaid on top of our cartographic representation. This is probably the closest that we have where InfoVis and cartography meet. So sort of the thematic maps that you've likely seen all over the news. So anytime there's an election, you've probably seen some variant of this. So usually this is some color or some additional overlay, like a scatter plot or a bubble chart that's overlaid on top of the map to represent some statistical features of the population, right? So this is sort of where we get an overlap between visualization and cartography as this kind of thematic representations. Related also are all the statistical graphic approaches. So you have probably a tool chest of these things, toolbox. If you are users, I guess maybe I should have asked earlier, but I assume a lot of you are R users. You've probably got a zillion different packages to produce a zillion different kinds of statistical visualizations. And these are great and will often be used as part of broader ideas in information visualization. Information visualization also feeds into some of these. So we will invent certain kinds of new statistical visualization approaches. And so there will be this kind of strong overlap. These are abstract representations of data, so they do fall within that category. They're often not interactive, and so they're static. They often require a lot of training to use, and they're highly focused on often narrow tasks, right? So they're very good for very specific things. And so we will use these ideas, but in our consideration, we'll often combine and augment them in different ways because our audiences tend not to be statisticians per se, right? So there are various audiences that we might want to cater to when we build information visualizations, especially for communication, that make visualizations like this maybe less attractive and less useful. Okay. So again, strong overlap, but there will be some differences that are worth considering. The other kind of related community that I wanted to bring up, because this is probably a lot of your experience with information visualizations for communication, is you will probably have looked at the New York Times or some other newspaper, either online or physically, and have seen infographics, okay? So these kind of very dense, self-contained stories embedded inside of the article or as the article themselves that convey information in an interesting visual statistical way. So this is like trains in Europe and sort of the length of railroad tracks and the different kinds of trains and so on. This is a very nice, visually pleasing visualization. It's an infographic. There is a story, there is a narrative. We'll talk about how this works a little bit later, but basically it walks you through an understanding of the underlying data. So there's a lot of different kinds of information on this. You can see the trains at the top with some data about them. You can see the maps. You can see the sort of this kind of donut charts with bar charts for different kinds of railroads in different locations. So there's a lot of information that's being hidden here and text all over the place that's walking you through how to understand this. This is another example of an infographic. This is like somebody's resume represented as an infographic. This is a dynamic infographic, so let me show you just how this looks. This is kind of a very visually pleasing one done by the New York Times. So it's a Sankey diagram for those of you who are unfamiliar, basically representing sort of how much of a population is being moved in to different buckets. So this is if they grew up rich, where do they end up? And there's other variants of this as you scroll down. So for poor children, where do they end up? Okay. So it's kind of interesting simulation where you're watching and engaging with the data in a very different kind of interesting way. It is part of a larger narrative. You can see as the little dots move, the counters are changing. So it's an actual simulation that's going on with some underlying, based on some underlying representation of the data. But this is a way to get people to sort of sit there and watch and like reason about what's going on, okay? So it's not just the text of the article. It is something that's kind of deeply engaging. It's animated. You really do want to see where these dots are going. But you get a sense, even if you don't sit there for a long time, you get a sense of sort of the colors and where they're going, just sort of different populations and where they're going to end up. The denseness of the different dots is easy for you to read, right? So even not knowing a lot of detail about this, you're able to do this, you're able to use this visualization for its intended purpose quite well. Okay. This is another example. This is from one of my favorite sites, The Pudding. I don't know how many of you have seen thepudding.org or thepudding.cool, sorry. They have a ton of visualizations. They're often like rooted in sort of pop culture. This is a visualization of rap artists and how many different kinds of words they use. Okay, so you have the artist, and so Aesop Rock has the sort of most, the largest rap vocabulary of any of the artists, and you have NF, who I don't know, way on the other end, and sort of this dense structure. It's a bee swarm kind of diagram. with little icons, for the people. So this is very cute. And there's like interactivity again to help you find certain people. So if there's a particular rap star that you want to find, you can do that. You can also find it. The article is essentially about the Wu-Tang Clan and sort of how lyrically interesting they are. So you can find just people in the Wu-Tang Clan and sort of how they were using different words in rap. Again, interactive, dynamic, very cool, fun. Yep. Yeah. Ooh. I think she was the prior one from the New York Times. Good. So the main tool now for producing these kinds of visualizations is a library called D3. So
sorry, you say library mean our library?
It's a JavaScript library. Okay. Sorry. If you're doing stuff on the web, you are largely limited to JavaScript for some of these things. I know there's Shiny apps and things like that if you're using R, but some of the more radical sort of things like this are probably done in D3. There's a little bit of a learning curve, I will warn you, if you try and do D3. I teach it to my students a little bit. It's useful, but it's not easy. So if you want to do this kind of stuff, which are a little bit one-offs, right? Like you're never going to reuse this for a zillion different applications. This is an aspect of information graphics design in general. Is it's a wicked design problem. It's a very specific, narrow problem that you will only do once. And there's no like perfect solution, whatever. There's a lot of features of wicked design. But again, you're going to make this kind of custom visualization and probably never use it again. Okay. The underlying technique, the Sankey diagram, is probably useful in other contexts, but this particular thing where you're simulating flows and things like that, has some temporal component, maybe not. Okay, so there's often not specific implementations of these things. You have to go find a library and then code them up. Okay. All right, I covered this one, I covered this one. There are also a ton of very bad infographic designs. This is a particularly awful one. So 3D pie chart, it's dynamically moved in space. I don't know, this is, we can talk about why this is terrible, but it's terrible. This comes from a site, WTF Viz, which you can sort of parse out for yourself. There's a lot of, I think it still exists. If not, they might have moved it somewhere, but that's a visualization site. There's a community on Reddit that does this kind of thing. I'm sort of tracking particularly awful visualizations. I suspect this was kind of a joke. I don't know, hopefully. But this is an example of what not to do in the infographic space. Just to summarize though, infographics, which we'll use concepts of this, tend to be elaborate, explanatory, self-contained. That is, you're reading them and all the information that you need to parse them is available to you within that context. So when you're going to the New York Times, you don't have to like learn how to use this new kind of visualization technique often, like by going somewhere else and reading a document about it. Everything is contained. There's a lot of information that leads you into how to read through it. Okay. They do use InfoVis techniques, but we can learn from them, and especially when we're talking about communication, we're going to come back to the structures that are really effective. So things that work really well in infographics tend to work really well for communicative visualizations as well. So the kind of narrative structures and storytelling that people use are going to be very useful. So we'll come back to that later. But it does tend to be sort of a slightly different community. Okay. So let me do this really quickly. Hopefully I don't need to convince you too much about InfoVis being good for something. It's good for a lot of things. We talked about sort of its cognitive boosting ability, exploratory data analysis. I don't like the word exploratory data analysis. Like, I prefer analytical data analysis. Exploratory means like you're not looking for anything, which is not really the case. People are not paid to explore, they're paid to find. Anyway, there's a number of different reasons why we visualize. The most famous example, how many of you have seen Anscombe's quartet before? One, or online, you can raise your hands if you want. A few people. Okay. A few. Okay, so Anscombe's quartet, for those of you who haven't seen it, is this very famous example by Anscombe, who wrote an article about why visualization is interesting and useful. He shows 4 different data sets. They have an X and a Y. Okay, and if you do some very standard traditional statistical analysis on them, you get that basically all these data sets have the same properties in these statistical contexts. So they have the same mean, the same variance on the X and the Y, they have the same correlation, same regression line, linear regression line fits them perfectly. Okay, so all these things arguably statistically are the same. But Anscombe says, well, this would be a mistake to understand these data sets as being all the same, because if you visualize them, the first one looks like this, and the second one looks like this, and the third and the fourth look like this. And suddenly you recognize when you visualize the data that these data sets are actually very much not the same. There's outliers in the two bottom ones, there's a nonlinear relationship, right, in the second one. So all these things are interesting and important, and you should have caught it if you had just visualized the data. So Anscombe's thing is that a computer should make both calculations and graphs, and both sorts of outputs should be studying. Each will contribute to understanding. So this is kind of the traditional thing that we teach all our data science students now, is that if you have data, you should visualize it, you should understand the distributions of it. You'll get information from the visualization that you may not have gotten just from applying standard statistical approaches, okay? So this is why we visualize at a high level for sort of this kind of understanding of data. How many of you have seen this one? One, okay. This is John Snow's ghost map, Broad Street map. So John Snow, famous epidemiologist. My wife is an epidemiologist. She loves this. As I said, we were just in London. She has a picture of herself using the Broad Street pump because she thought that was awesome. So this is a map of malaria deaths in London in the 1850s. All the dots represent a death, okay? What John Snow had done kind of as an early exercise in epidemiology is he went and knocked on doors and figured out where people had died and plotted them out. And there was not an understanding of cholera, that's not malaria, cholera, where people were dying. So there was not an understanding of how this was happening, like what the transmission mechanism was. And what Snow had figured out and conveyed through this map is that there was a lot of deaths that were centered around this particular pump marked with an X on Broad Street. So there were a lot of other X's, a lot of other pumps, water pumps that people were using. These were shared pumps in the city. The deaths were highly clustered around the Broad Street pump. It's kind of in the middle, X. And if you remove the handle, which is what they did, the deaths stopped. Okay, so this is kind of an early example. It's a little bit apocryphal, but this is an early example of epidemiology in action using visualization. Okay, so the power of visualization. It's not clear whether he used this actual map to do this analysis or whether he was just trying to explain to the public what was going on. So whether it was the tool for analysis or a tool for communication, not entirely clear, but it's a very nice example of visually striking, where you can see this kind of dense structure, this pattern in the data that you could see through the visual information that you might not have seen through other kinds of statistical analysis. Okay, so I gave you sort of a long list earlier of why we visualize. I want to talk about 3 high-level functions. So recording tasks, analysis tasks, and communicative tasks. This is kind of the 3 main areas of work within the information visualization community. And I would say largely biased to the second 2. It is not the case that every visualization must exclusively fit into one of these categories. There's often situations that you'll see where we will have a visualization that is both used for analysis and for communication, or both for recording information and for communication, or for analysis, right? So there's often overlaps between these. But it's a useful distinction sort of to think about. The record is basically using visualizations as an actual record of data. So instead of recording information in a table, we might record it in a visualization. And often there's a better representation through a visual mechanism of the underlying phenomenon. And so we'll do this. This is an early example from 1626, a little bit of a sci-viz, but this is sunspots that were recorded. It's a record of the data. You can go look up the information where sunspots were in any particular time of day. For analysis, it's not clear what its application is, right? It is a tool sort of as a record. The principal one was kind of the main one that probably I would guess most of you do as a day-to-day job as analysis. Although most of your day-to-day experiences with visualization, I'll argue, is communication. I'll talk about that in a second. But analysis tasks are Basically, the use of visualizations to amplify cognition, often for pattern finding. And the reason they work so well is that when information is translated into visualization, we don't have to remember things quite as much. Okay? We don't have to look data up and move between rows in a table or cells in a table to find particular pieces of information. The representation of data in a visual form on paper in this way allows us to very rapidly do different kinds of things that would be tedious and annoying otherwise, and maybe very impossible. So this is an example of a memory aid in action. This is not a visualization memory aid, but it is one that sort of conveys this idea well. If I ask you to multiply these two numbers in your head, some of you may be able to do this quickly, but most of you are probably trying to at least mentally reach for paper, right? You're trying to break this problem up as you have been taught to do in elementary school, sort of break it up into a long multiplication problem and sort of do this, right? Our inability to sort of execute these kinds of things in our head and our desire to break them down into sort of smaller steps that we record on the page is kind of why visualization works. So this is another famous old example that Tufte loves. This is a train schedule. Okay. If I asked you to remember how long it took to get from different train stations in France, and when trains came and how long it would take for a specific train to get from one station to the next, this would be a very dense data table for you to keep in your head. And for you to tell me sort of what the average length of trains to get from Paris to Dijon would be, or how to get there, like that would be very challenging for you if it was represented as a table. When it's represented in this way, this enables analysis, right? So these are stations represented on the y-axis, time represented on the x, and the train is kind of this line that moves from station to station, and you can follow it, and the intersection will tell you when the train arrives at a particular station. You can also see when trains are sitting around and not doing anything for a while, waiting for customers. So there's a break in service here. You can see if the trains are going in one direction or the other. That is perfectly readable and legible through this visualization. So isn't this kind of a great way to convey very dense information in a visual format that is easy for you to decode? So that's kind of the power of visualization in the context. People have used visualizations before there were even calculators. So this is a nomogram. It's a very particular kind of visualization techniques where you're actually doing calculations using a visualization. So this is a nomogram for people who are calculating risks of contamination of a food factory. And so what you would do is, think of this as like an old slide rule kind of thing, right? So you would look at number 1 over here in this corner, and you would answer like, what's the likelihood of occurrence? So you basically make a determination on your own, and you put a little X where you think this is. And then you say, what's the manufacturing control in this factory? And you mark another little X. And then you draw a line between those, and you see where it intersects. And whatever the value of that is, gets transferred into the next little calculating visualization. So 3 becomes 3A, and then you repeat this over and over and over again until you get some risk calculation at the end. So when you get to step 12, you have some values that were determined by sort of drawing on this visualization. People don't do this much anymore, right? Clearly, but it's kind of a cute, interesting old technique. So, okay, one last example from the analysis space, and this will be a sort of foreshadowing about why we want alternative visualization techniques. So this is a visualization of sunlight over time. Okay, you can see certain kinds of seasonality in the data, right? The sun comes up, the sun goes down, right? But there are other kinds of seasonalities at play here, like over time that the sun comes up and goes down at different times over the course of the year. Right? And that is very hard to see in this particular visualization. So the high-level pattern is easy to see in this time series, but the other kinds of patterns are much harder. And so people have invented alternative approaches. This is visualizing time on a spiral. So imagine taking this time series and overlaying it on a spiral that is expanding from the middle out. And based on the denseness of the spiral, so sort of how much the angle of rotation is of that spiral, will reflect different kinds of seasonality that you want to capture. So in an actual implementation of this, you will be able to set different kinds of seasonality parameters that will directly map to different kinds of spiral behaviors, and you will be able to see different patterns in the data. So if I wanted to see the pattern every 24 hours, I would use one particular spiral configuration. If I wanted to see a pattern every 4 months, I would use a different spiral configuration. And you would see sort of a black line moving across from the center out if there's a good pattern. Okay, so when there's this kind of alignment, so right here you can see an alignment of all the yellow where the sun is up versus where the sun is down. This is kind of a 24-hour periodicity. If you use other ones, you'll see other kinds of patterns, and you'll see kind of a black streak going outwards, or kind of a piece of the black pie moving outwards when there is a pattern in the data. So if you're trying to understand seasonality, this is a very interesting technique. And the interactive versions of this actually allow you to move a slider until you lock into the seasonality that works. So yes, there are statistical techniques to determine seasonality, but this is a very visual interactive way where all you need to do is move a slider from left to right and identify those points in the data where seasonality is happening. Okay, so an alternative approach, and this is what I want to convey to you, that there are some specific kinds of tasks that we will come back to later that are best served through alternative visualization techniques. So the standard approaches, which are great for a lot of tasks, may be made better through alternatives. Okay. Just to summarize the analytical part, the goal of analytical visualization is to find patterns in the data. So either you are trying to find the pattern, it's finding patterns. That's probably the best way that I can put it. It's finding patterns in the data. Either you have some mental model of the kinds of patterns that are interesting for you. Is it a normal distribution? Is it a Poisson distribution? Whatever. And you want to see whether the data fits. Okay, so you're trying to find whether there's a match between the pattern you have in your head versus the pattern that you have in the data. Or you don't necessarily understand what patterns exist in the data, and you're trying to make the pattern. So it's a matter of pattern classification in the data. Okay, so those are kind of the things that we do with analytical visualizations. Communicative tasks are when you turn this around and you've found some interesting thing about your data. You have some insight, some answer, something, and you want to convey that to some audience. So the communicative task assumes, rather than you working with a computer, that you are going to use the computer or some mechanism to build a visualization and convey it to somebody else. Your boss, the readers of the news, whoever it is, they will be the people who will be reading the information, and they will not have the same underlying knowledge as you have. Okay, they will have a very different set of expertise. So when we talk about communicative visualizations, we're very concerned with adding features to the visualizations, even if they're standard statistical visualizations, adding features to them like annotations that will allow the reader to decode the message. So this is a very famous example from Playfair, William Playfair from the 1700s. He was one of the earliest people to use visualizations in this way. He kind of credited for the invention of the pie chart, although there are some other examples in the space. But he wrote this book basically about trade. So this is European exports to Denmark and Norway. And you can see the trade deficits are very clear, right? He's using color, green and red. We take issue with that today, but right, there's a lot of information being conveyed here in a very simple way for an audience that is maybe not as literate in statistics to be able to parse this and understand what's going on. Okay? I wouldn't need to necessarily label this quite as clearly if you were an expert in trade policy. Like you've probably seen these all the time. But if you're not, okay, this is where we start adding annotations and using other kinds of little hints in the visualization so that people can understand them. The more kind of fancy versions of this, so people have built all kinds of software and tools. This is Spotfire. It's a piece of software that doesn't exist anymore, but it's kind of an example of these interactive visualization systems where people would do presentations with visualizations. So this is one extreme from the 1700s. This is another extreme from the 2000s. And there's everything in between now. And people make visualizations that are communicative for the web, for example. Again, a very early example. This is Nightingale's diagram of causes of mortality. it's not a very good statistical visualization. It's not that easy to read. But this is what she used in order to convey the number of deaths that were happening for the army of the East, right? So this was the way that she would communicate with the generals. It's a very pretty, interesting, compelling diagram, a very interesting representation. It takes some work to parse. Okay, so it's not necessarily that it's easy, but it does convey the information in a way that gets people to read it. So this will often also be a characteristic of communicative visualizations, is not necessarily simplifying it, but is getting people to engage with it in a way that they will get the information that they need. You will be able to effectively convey your information so that they've learned it. If you've ever tried to teach students, this is why we're going to come back to learning objectives. If we're ever going to try to teach students, you've taught students, I assume many of you have taught classes, have sort of given lectures, whatever it is, you have an audience, right? You need them to pay attention and you need them to understand something at the end of the day. And the tricks that you will use, okay, doing a song and dance routine on stage, those are tricks. They have nothing necessarily to do with the underlying message, but they get people to listen sufficiently so that your message is conveyed. So this is often a part of communicative visualization. This is another example. This is a visualization of the network structure of the internet. This one is a little bit weird. Like, what is it that I'm trying to convey in here? Okay, so this often falls into the more art version of communicative visualizations. It's not obvious like what the intent is here, other than to convince you that the internet is big and interesting and complex. It's spaghetti. It's a spaghetti diagram, right? We can't read anything out of it. So there are versions of the outliers of communicative visualizations that I don't want to belittle. Like, they're great and they're awesome and I've done them myself, that are not necessarily intended to convey information, but rather to like inspire you or act on some other artistic objective. Okay, so these are kinds of the ranges of things that we talk about when we talk about communicative visualizations. Everything from the very simple and obvious to the more complex and dynamic. And we pick these based on sort of our intent and what we think will be the most effective when we're talking to our audiences. This is a non-effective, very ugly visualization. There was a website, I think that it's now a Twitter or Blue Sky instance rather than Tumblr, but there's a person who basically tracks all use of visualizations on the Senate floor. They're not allowed to use dynamic interactive visualizations, any computer screens, so they often print out these massive boards that are often embellished with some craziness on them, like the American flag, because that gets you to pay attention. So there's a lot of these, and some of them are particularly bad. There have been, of course, politicized attempts to use visualizations. So this is, I'll give you a guess. Like, this is Obamacare. Who do you think made this? Republicans. Very ugly, complex visualization. I'll show later the response to it. I think I have it in a different slide. It is very political in nature, right? It is using visualization to convey political beliefs, okay? Which is fine. Not every visualization is neutral. And I'm not going to tell you that you should make all your visualizations neutral, because I don't believe you can, but you should at least understand what you're doing when you're doing this. Okay, so unlike the goal of analysis, the goal of communicative visualization is to teach something, or at least support some kind of teaching. I want you to walk away and have had some cognitive change in your brain where you recall something or are able to do something when you've looked at a visualization that I've produced with the intent of communication. Okay, so again, it's a different task than analysis. At the root of all these things, though, is that visualization is about comparison, okay? So the visual system, what your brain is good at, is basically comparing things. Is it bigger? Is it smaller? Is it up or down? Is it there or not there? Like a pattern, not like a pattern? All right, so that's at the basis of every single kind of visualization, is this notion that all we're trying to do is support some kind of comparison. So all the visualizations that I've shown have a kind of comparison element to them, whether they were analytical or not. Okay. Where this becomes challenging, and what I'm going to talk about for probably the bulk of this conversation, is the choices that we have to make. So we want to support this kind of comparison. We want to support the kinds of comparisons that are most useful for the analyst or for the reader of our visualizations. but we have lots and lots of choices often. So how do we pick? So even something as simple as this, like the numbers 12 and 7, if I wanted to visualize these two numbers, there are a zillion ways I could do it. The simplest that you might imagine is just using a bar chart. Okay, this perfectly conveys this information. But there's a zillion other ones. All these visualizations represent a comparison between 12 and 7. And there's more. You can probably imagine drawing more. This is often a task. So I would have done this in person, but it's a little bit harder to do online. Usually I have my students try to draw, like I give them the numbers 12 and 7, and I have them draw this on Post-it notes. And we put them on the wall, and we sort of see the hundreds of different alternatives that they can come up with. It's kind of fun. I see some chat messages. Were there questions? Okay. Any questions from the room? I realize I'm sort of barreling through a lot of this, but feel free to stop me. Okay. So how do we think about our choices? How do we think about what we're going to do and the best tool that we're going to use? So the way I like to think about it, and I teach my students to think about it, is it's kind of a puzzle where there are different kinds of puzzle pieces that will fit well. And our goal is to basically have a collection of possible puzzle pieces that we can slot into our problem. We will use the specific tasks of the person in the domain, and I'll show examples of this in a moment, specific questions that they have, specific needs that they will have. Those will produce a shape of what is the appropriate puzzle piece to fit in. And that will be determined by the data or the underlying problem that they're trying to address. So the goal here, when you're looking at information visualizations, is to take away as much of the generalizable ideas that they have so that you can sort of use them in alternative settings. So as I show you visualizations, as I introduce examples, I want you to sort of take away the abstract variations of these and like keep them for yourself as things that you can slot in later when you have problems that are sort of unique and interesting and different. I will warn you, a lot of the examples that I use are old, like considering they're in the information visualization systems. They're examples old. They're from like the 90s or 2000s. So a lot of the videos you'll see are kind of older. And my students always complain about this, like, why aren't you showing us new stuff? It's that the new stuff tends to have like 50 million bells and whistles and hide sort of the underlying idea. So you'll see in the examples that I'll show is I tend to pick older ones because it's very clear what the basic idea is rather than the complexity of all the like, drop down menus and icons and whatever. So just as a warning and as a, indication, there are many, many modern information visualization approaches. I just want to warn you that some of the ones you'll see today are old, okay? All right, so information visualization, let's talk about how this works in the brain. So in the brain, we have some data, so we have some questions, we have some insights, and what we're going to do is a practice called encoding. Okay, so encoding takes the data, questions, and insights, translates them into a visualization, and the hope is that the human being looking at this visualization will be able to parse the visualization and exactly understand the data, the answers, the insights from that. It is a kind of compression technique that we are applying. We are taking data and we're compressing it into a visual artifact, and we're hoping that someone can decode that effectively. Okay. The problem with this assumption is that there's actually a lot of things that are limiting in the human brain and the human eye that prevent us from doing a very clear translation. What we're going to have is a noisy translation of the underlying data. Our ability to decode exactly what it was that we were trying to convey will be limited by lots and lots of properties of the human mind. So I mentioned a few things of notation. I mentioned encoding. You'll often hear me talk about nominal, ordinal, or quantitative when I talk about data. Nominal data is like categorical data. So this is a categorical visualization of some very tall skyscrapers. So I'm just showing you that there are these categories of skyscrapers. They're all different. You can tell that they're all different. That is a property of nominal or categorical data, is that you are able to tell that these things are different, distinguish between equal and not equal. Ordinal means that you're able to rank them in some way. So you can distinguish different, you can do the same thing nominal does, but you can also rank them. It's not to scale, so you can't tell me how much bigger one is versus the other in this particular visualization, but you can tell that they're different, and you can tell the ordering. Quantitative is kind of the most information-bearing idea. This is to scale with numerical items listed. So if I ask you to tell me how much bigger is the One World Trade Center from the Chrysler building, you're able to do that. So you're able to rank, you're able to tell different from not different, and you're able to do mathematical computations. So this is sort of the three categories that you'll often hear me mention when I talk about data. So I just wanted to introduce you to these three concepts and sort of the differences between them. So nominal, ordinal, and quantitative, okay? But stop me if you forget and I use some other word that you don't know. The other thing that I mentioned already is encoding. So you'll hear me say encoding a lot. So the key principle is that visualization is communicating data by encoding data as marks. So marks are anything that you put on the screen. Lines, bars, circles, whatever it is. Okay, so either the marks themselves or the properties of the marks, like their color, their size, their location, will convey some piece of information. So the task of encoding is taking data and translating it to marks on the screen. If you've used ggplot, this is probably a familiar concept to you. You're taking data, you're deciding which mark to use, and then you're doing some mapping, some encoding between the data and some characteristic. We'll sometimes call these retinal variables, things that you can decode through your eye, but visual characteristics is fine for now. Okay. There's many choices for each mark, so I won't talk about this that much, but people have done scientific studies to sort of figure out the optimal representation of different kinds of data sets so that you are able to decode them accurately. We'll come back to this a little bit in a moment, but for quantitative data sets, if you can use position, like XY coordinates, that's better than using color saturation. Okay, so over here, you sort of see the differences in these encoding approaches. And different kinds of data are better using different kinds of things. So density is good for ordinal, but very poor for quantitative. So depending on the kind of comparisons you want to support, you would use different kinds of visual properties for your marks. Okay. High level, we'll come back to this in a minute, but this is when I talk about properties of marks, these are often the things that we have to play with. So marks represent entities, so things, properties of things, relationships. So you can have, if you had a social network diagram, a mark like a line between two nodes representing people means there is a relationship between them. So there is a meaning to the marks. Yep, sorry.
Can I actually go back to
Yeah, of course. McKinley.
Oh, I got it right.
Okay. The slides are on the GitHub, so you can find them later too. Oh, for anyone who's interested, so Jock McKinley, who invented this many years ago as part of his graduate work, later became one of the co-founders of Tableau. So if you use Tableau, Tableau does a lot of this stuff automatically for you. So if you drag a quantitative variable, it goes and looks this up in the table for you and sort of makes a decision about the best way to do it. Okay, so marks will express some information through this encoding. So if we have a simple table, like name and score, the visualization like this one expresses a set of facts. So this is the other piece of vocabulary that I'll use a lot today that I want you to know. So expresses is what information is decodable when you look at the visualization. So the visualization expresses that A is 1, B is 5, C is 2, that B is 5 times larger than A, that C is 2 times larger than A. These are facts, information facts that can be derived by you looking at the visualization. So these are facts that are expressed. So they could be insights. They could also be the answers to questions. Okay, but this is what is expressed through this visualization. This is a visualization that expresses the relationship between mileage and price. Okay, so these are cars. Each of the little pluses represents an automobile. This is old, from 1979. You can see the price of the car. You can see the mileage, the MPG that it gets, miles per gallon. Okay. Very expensive cars, very heavy, tend not to do very well. This visualization expresses the correlation between these things. It does not express the relationship between specific cars. So if I asked you about the Ford and the Toyota, that is not expressed in this visualization. You are not able to answer questions about this. This visualization expresses the relationship between mileage and price and supports the comparison between cars. Okay? This expresses a limited set of facts. This one expresses more. This one may express too much, depending on what it is that you're trying to do. This is hard to read. There's overlapping labels. Okay, so depending on the task, this, which is less expressive, less information is being conveyed, may be better than this. Okay, we'll talk about that in a second. So again, overexpresses if we don't care about specific cars. This visualization also expresses the same data as this one. The same information is being expressed. You will be able to decode and answer questions for me. The same questions you'd be able to answer using this visualization, you'd be able to answer using this one, but it will be less effective. I don't know why it keeps doing this. It will be less effective for the purposes of determining a correlation. You cannot see the correlation here. So if my intent was for you to understand the correlation between price and miles per gallon, this is a great visualization. This one's terrible. Expressive, but not effective. Okay? So what is expressed here, what is not expressed here? Looking at the visualization, what is expressed is that there are 4 bars, and you can probably rank them because you know how to read a bar chart. But what you can't tell me is sort of how high they are and how much different they are from each other. This might be negative numbers for all you know. Okay. So the things that are expressed are, there are 4 things with 4 different values. But beyond that, you can't tell me anything else. When we talk about expressiveness and effectiveness, this is a good example, okay? There is a pie chart at the top and a bar chart at the bottom. Which one is more expressive? Yeah. It's a good guess. Which one's more? The bar chart. Okay.
I can refer you to visually evaluate angles at different orientations.
Okay. So it is a reasonable assumption to say that the bar chart is better. Okay. So people often go, bar charts are better. I'm going to argue for a moment that these things are equally expressive. The same information is being encoded in both. If you were able to read angles well, you'd be able to decode the exact same underlying data set by looking at these 2 visualizations. But you will not be able to do it as well. So this is the difference between expressiveness and effectiveness. Equally expressive, more effective for certain tasks. If I wanted you to tell me what the difference between these 2 bars were, you would be able to tell me, sorry, the difference between E and D, you'd be able to do that much better with this visualization. If I asked you, if my task for you was, what fraction of B is the whole, you would do much better with the pie chart. So for part versus whole comparisons, more effective. For plain comparisons between A and B, this one, more effective. Equally expressive. Expressiveness is about your ability to decode it back into the original data. Effectiveness is how well you're able to achieve a certain task with it. Does that make sense? Any questions online? This is often like the thing that I have to come back to a bit. Okay, all right. Are they disagreeing with me?
One person just asked. This person asked, can you say that one more time? I'm not sure exactly what they're referring to, but.
Okay, one more time. I'll assume you're talking about this particular thing. So both the pie chart and the bar chart are encoding the exact same data. So we know when we're looking at the pie chart that there are 5 different things and they're labeled. So we have A, E, D, C, B. We know the total size of this is 17. If we were able to read angles well, we'd be able to tell you that A was 5. Okay. we're not able to do that well. We'll come back to that in a second. So you are, in theory, able to decode a particular data table out of this. The same data table can be decoded by looking at the bar chart at the bottom. So if you think about the columns, there's a column for name and a column for value, okay? So they're equally expressive because I can decode the same underlying data from them, the same column headings. They are not as effective for different kinds of tasks. So because we are unable to read angles well, relative to the lengths of bars, if I asked you how much bigger is A versus B, you will not be able to do that well. So that for that task, it is less effective to use a pie chart than a bar chart. If it's a part versus whole comparison, what fraction of A is, what fraction of the whole is A, you will be able to do that much better with the pie chart than the bar chart. So for specific tasks, one or the other may be more or less effective. Equally expressive, different effectiveness for different tasks.
So we got 3 questions here.
Okay.
I'll take them. So, follow up to what you just said. Can you just clarify, just put a fine point on what the exact definitions of expressiveness, effectiveness are? You just said it, but if you could just sum it up quickly, that'd be great.
Expressiveness are the facts, or the statistical data facts that one can decode from the visualization. Okay. Effectiveness is how accurately we can do that.
Then the next question is, would one ever want something that is more expressive but less effective? Like, can you give an example of that? Maybe.
So, okay, some people will disagree with this idea, but we've written a paper on something called desirable difficulties in education, where we make visualizations a little bit harder to read. And the reason we do that is we want the students to sit there and puzzle over the visualization for longer. So we've made them on purpose less effective, because that difficulty will increase engagement, and that engagement will increase learning. So in that situation, that's an example of where I have used less effective visualizations to make a point for an educational purpose.
And this person's asking, so it doesn't make sense to say a graph is more or less effective without specifying the task itself.
Correct. So that is absolutely correct. So if I ever say more effective, you should always think in your head for what, and if I don't say, you should ask.
Last one here is, what do you think about the stacked bar chart?
For certain tasks, it's very effective. It depends on the kind of data and the kinds of questions. So it's fine. If you're often a stacked bar chart is great for sort of, you need a part versus whole comparison, and additionally you want the ability to decode specific pieces of data like the height of bars. So it is less effective for anything that is not at the baseline. So the things stacked on top are harder to read. So there's a trade-off that's being done there. Right. So no visualization is bad per se. It's just bad for specific things and good for other things.
One last question. Can people online hear my voice? I'm not using the microphone. So if you don't answer, I'll have my answer. But if someone out there could tell me if you're picking up my voice, okay, that'd be great. Okay. I think we're clear on the chat.
Sorry.
I just had a follow-up question. You said, like, for your students, you said, like, sometimes you use a chart graph that is maybe less effective, where people have to puzzle a little bit more. So would you say that you have to find, like, the right sweet spot of effectiveness so that people kind of memorize actually the data that you want to convey?
Yes, right. Yeah.
If it's too easy, then people maybe
Absolutely.
then look away and don't really memorize the data.
Yeah, so just for people online, the question is, like, do you have to find a sweet spot, is right, like, of where sort of optimal difficulty where people will memorize it versus, so if you make it too hard, they'll quit and sort of leave, and that you don't want that. If you make it too easy, they may just like skim through it, just like if you have an easy reading, right? Like you may just like sort of in one ear and out the other. If you have kids, or you can remember back to when you were a student, practice, right? Like this level of difficulty and increasing level of difficulty in problems that you try in order to effectively learn something, that was needed for you to learn certain kinds of material. It's the same thing with visualization. So visualizations as an intervention in learning, you have to sort of make a sweet spot determination. And it depends on your audience, it depends on their skill, it depends on a lot of things. So there's no easy way of doing this. We'll talk about some ideas of how to do it, but yeah, you have to sort of understand your audience well to do this effectively. The Andrew Gelman, who's a statistician at Columbia, he has this theory which I like. So he talks about visualizations as he distinguishes between New York Times visualizations and USA Today visualizations. So New York Times, his argument is that the audience really likes puzzles. They're the crossword puzzle doing audience. So the New York Times can basically have these really, really complicated visualizations because their audience, they know, love the payoff of sitting there and puzzling through the information to find these little nuggets of hidden information. The USA Today audience, he argues, they just need to read information quickly. Like they just want the little bar chart in the corner of the newspaper. They're just like quickly consuming information. They don't have time, no interest in sort of those puzzling things. And so the things that the designers of the New York Times are able to do and are willing to do and can do are very different than what the USA Today designers will do, right? So that's kind of this difference of like a sweet spot, but it's a sweet spot based on your audience. Yep.
No, I'm good. Yeah.
Do you have a citation that comes to mind for that? Because I feel like I struggle with that in my work of like, in the mobile health space, there's a lot of literature suggesting that people most prefer the bar chart, which I think is so boring, especially if you're like showing it to them so many times over the course of, you know, like a 30-day intervention period or something like that. But I'm struggling to like find something to cite that says, no, like this is, it's like a design thing too, right? When you show someone something once and have them rate something, right? Maybe something that's more understandable.
Right, that's right.
They're actually engaging with it.
Yeah, so it's how much they're willing to also learn, right? There's a learning curve to certain visualizations, so are they willing to learn it? But yes, I can point you at some things, but after like, so Gelman has an article and I have a paper I can share with you too. Just, yeah, remind me.
I found this, for example, dealing with executives, they're overwhelmed. Their preference is generally fire hose them because they don't have time. And some put it, if we need you to slow down, we'll tell you. And they like standardized graphs because you may be reviewing 30 measurements now within 5 minutes. So they're simple and standard. They don't want to have to learn a new story or technique for each page.
Yeah, I think that's right. So I think if your audience needs to read things very quickly, an airline pilot, right? Like if you're looking at a dashboard on the plane, you don't want to like figure out some new visualization technique.
Standard thing on a lot of these graphs is for each graph, you put an arrow pointing in the way that's better. Because it may be flipping from 2 up, you want up, and another one you want down, then 2 up, and so on.
Yep. So there's very easy ways of amplifying these so that they're more easy to read and take things away from. So they're in dashboard design, like when you really need to do decisions quickly, right? Like a Bloomberg terminal, like you don't want to sit there and puzzle through visualizations. You want to be able to execute on decisions quickly. And so there's a lot of affordances, a lot of design decisions that are made to support those kinds of quick decisions, and that would include also like presentations to certain people whose time is valuable or who think their time is valuable. Great. Okay. Let me wrap this little section up, and then maybe give everybody a 5-minute break. I feel like I've been rambling for a little while. What I'm going to talk about next, so after this 5-minute break, is like, how do you pick? So like, how do you know, like, what is it from the theories of perception and psychology that would tell us whether one visualization technique is more effective than the other? So all these are equally expressive again. You have bar charts, you have these heat map kinds of things, you have these little iconic representations. They're all showing the same information of the underlying data sets. They're all equally expressive, but how do we decide about effectiveness? And that's what I want to focus on in a few minutes. So let's take a 5-minute break. People can get up, stretch, go to the bathroom, whatever, and we'll come back in 5.